Homework 11, page 161, section 3.5. We're moving into section 3.5. Like I just said, we're going to get out of trig because you're going to have plenty of stuff with trig. You'll get plenty of practice with it. I do want to move on. So that's number 7 through 33 odd, 47 through 53 odd, 73 and 84. That's a total of 20 problems. And like I said earlier, that's probably going to be standard. About 20 problems per homework. Now on number 73, I want you to show your work and or reasoning. Okay, and for this it has this notation D and then a number up here. And so D with a number and then some function right there means the second derivative of. Okay, or so like D2 of some function f of x means the second derivative. D5 of some function is the fifth derivative. Okay, and so you'll need that there. Okay, so that's really all there is to that. Should be straightforward. Okay. Any questions before we start today? I don't think so. I actually do have some time for questions. So the one time we have time for questions. Okay. All right. So let's do this. What are we going to do? Tell me what to do. I want to find the derivative. Given that that's h, I want to find the derivative. What do I need to do?
It's 2x squared plus 1 times 2x squared plus 1, and then you can.
Yeah, right. You would think, okay, we're going to multiply this guy out. This is the same thing as 2x squared plus 1, 2x squared plus 1, and then we first outer inner last, which gives me what? Or you could do a product rule. You could do a product rule.
That'd be harder. Right?
It seems like that would be harder because, yeah, like I could just imagine it, right? You're going to have the derivative of something times this thing plus the derivative of something, or the thing times the derivative of... It's usually with polynomials, it's almost always faster to just multiply them out. Sometimes it's not, but usually is. So let's just multiply it out.
4x to the fourth.
4x to the fourth.
Plus 4x squared.
Right, because of those two, so it's a total of 4x squared.
Plus 1.
Plus 1. Now we can take a derivative. And what do we get?
16x to the third.
Yes, because the 4 jumps down, hits that 4, and becomes 16x. We decrease that by 1. Okay, then
8x.
Plus
8x.
8x. And that goes to 0, and so we're done. Actually, I want to give myself some room, so I'm going to put this up here, plus 8x like that. Okay! There you go. Now, what if, though? That was pretty easy. That was pretty straightforward. But what if h of x weren't squared? What if it were to the 20th? You'd think, well, okay, binomial theorem, we'd expand it, and it would be really, really, really bad. But maybe there's a better way. And it turns out there is a better way. Because so today's topic is what's called the chain rule. And so we did a product rule. What happens when you have two functions that you multiply together, that are multiplied together and you want to take the derivative? We have the sum or difference rule, which is when you have two functions that are added together or subtracted, and you want to take a derivative of those. Well, the chain rule occurs when you have a composition of functions. And you'll notice that we could think of this function as one function inside of another function, right? If we think of f of x as just being the outermost stuff, which would be this stuff squared, so I guess just whatever the input is, then you take it and square it. And then the inside stuff here would be, stop looking at your, that is disrespectful. Please don't do that. It's alright, just don't do it. Let's try to pay attention, okay? And the inside stuff is this stuff, right? Then we could see this as a composition of two functions, right? Now, the chain rule tells us how to deal with derivatives of things in functions inside of other functions. And so, okay, let's figure out what that's going to be. So let's see. If I take the derivative of a function inside of another function, just by definition, this is what?
The
limit
as h goes to 0.
As h goes to 0 of
f of g of x plus h.
f of g of now it's x plus h. That's what you're plugging in, right? Minus f of g of x. Okay. All over h. Now, if we're actually doing it with this one, we'd be able to do some calculations and stuff. But here in general, when you just have two functions, what do you do with that, right? Like, the idea is hopefully we could do some work and end up with something that's easier to deal with rather than having to go into like actually plugging this thing into here and figuring out a limit. So one thing I want to do, the way I want to start by trying to figure out what this is we're going to rewrite. So, well, the first thing I do want to notice is there's two things going on here. Like, x is going into a function g, right? And then g, whatever that output is going into a new function f. That is, whatever the value of x is goes into g. And then that, as an output, goes into the function f. And so, it's not so simple. Like, if this were just f of x plus h, we could draw this nice little picture and get an idea of what's going on, right? If it were just forget about the f of g of x. If this were just f of x, you'd say, well, you go to x and you go to x plus h. And you set up this difference quotient, right? You have f of x plus h, f of x, and you set up your difference quotient, you could see what's going on. It's not so simple now, because now we have two functions that we're dealing with here. And to be explicit, what's going on is x is going into g first. So this picture's not going to help us because that's not what's really going on. But x is going into g. So we have some function g. Maybe it looks like that, and here's my g. And I'm plugging in some x into it. And I'm getting out a g of x, and then I move over to x plus h. Plug that in, and I get a g of x plus h right there. Right?
Yeah.
Then we're taking those values and plugging them into f. So what we're setting up over here is we're saying, okay, here's my, let's say it looks like this. I'm taking whatever that value is, or wait, no, we'll take that value. Taking g of x and plugging that in and getting an f of g of x. Then I'm taking that value, plugging it in, g of x plus h, and out pops f of g of x plus h. And then, remember though, this isn't just h. Well, I mean, it is, but where that comes from is the difference, right? X plus h minus x, right there. Right? And we simplified everything by saying, let's just call it h, right? But really that's what's happening, right? And as this value gets closer to that value, right? As that happens, this guy comes this way. And so this guy goes that way, and we kind of have this double thing going on, but just, so again, it's not, with this x plus h stuff, it's kind of hard to use this definition of the derivative. Now remember, there are a bunch of different ways that we could write this same thing, right? Let's recall one of those ways. We could say, instead of doing all of this, we could say, this is the same thing you would get if you did this. The limit as y goes to x of f of g of x minus f of g of y, right there, right? And as one goes to the other, I'm just making sure that that matches up with that and that matches up with that, right? Because of the slope thing, right? you have some x here, and you have some y here. And if this is the point that you care about, then you're going to let y go to x. And so as long as you have the if you have y minus x, then you'd need the f of g of y, first, f of g of x. And as long as they match up, they're good, right? Because this is the same thing as doing it the other way. You could have gone f of g of y minus f of g of x, y minus x, right? Same thing. And you could see that by pulling out negatives or whatever. But as long as we keep that in, but that's neither here nor there. That's not really what we're talking about. My point is, this is the same thing as that, right?
Yeah.
Yeah, I'm just kind of calling y x, or I'm calling x plus h y. And in both cases, the limit is going to the same place. Right? Everybody buy that?
Yeah.
Okay, all right. So if that's the case, now let's kind of reconsider what's going on here. So everybody agrees that this is the same thing as that, yeah? Okay, then what I'm going to do, I'm going to go ahead and get rid of the one that's not really going to help us much. And I'm just going to write this one right here. This is the same thing, the limit, as y goes to x of f of g of x minus f of g of y, x minus y. Okay, so that's the same thing. So that is the derivative at x. Yes? Now, don't hate me for this, but I think that this will, I think that the way I want to talk about this, it will be easier if we do what I'm about to do. And don't hate me for this. But let's instead of at x, let's just call this place x1. And so, is that the same?
Yeah.
I've just renamed x to be x1, right? Like, I've renamed it. There's nothing different going on here. Trust me on this, it's going to help a little bit if we do it this way. I think, at least. Okay, so that's still the derivative of this function. And after we figure out what it is, I could just rename x1 x. And it's exactly what we're looking for, right?
Yeah.
Okay. And don't hate me for this, but I could rename y anything I want as well, right?
Yeah.
In fact, I mean, if I wanted to, I could rename y x2. And as long as I just make this, and then if I need to, at the end, I could just say, okay, wherever there was an x2, or wherever there's an x2, I could just replace it with a y, and everybody's fine. So everybody still believe that this is the derivative of this function at x1. Okay, I really haven't changed anything. I'm just being a little tricky with how I'm writing it. Why am I doing that? Well, because it's going to make what I'm about to do a little bit more comprehensible. So, again, these are just names. There's nothing crazy going on here. But now, let's see what's going on with this. What's really happening? Well, again, in this function, this is a composition of functions, just like this is a composition of functions. And if I said, evaluate this guy at x equals 2, you would take your 2 and you'd plug it in, right? You would take your 2, you'd plug it in and do this stuff, and then you'd get some output. I guess it would be 4 times 2 is 8 plus 1 is 9, right? You'd find a 9 as your output. What have you done? You've taken your input. This is G. You've taken your input, you plug it in, and you get some output. You got your 9. Okay. x2 is the same way. You plug something in, and you get g of x2. But that is just some number. Let's give it a name. Don't hate me for this. We're just going to call it g1. Everybody buy that?
Yeah.
Okay. Yeah. And this is just, again, some number. You've taken some number, you've plugged it in, you've gone some distance beyond 2, maybe 2.01. And you plug it in and you do some stuff with it, and out pops a 9.07 or something, right? And so whatever that number is, we're going to call it G2. And so now that goes into your next function. Those outputs go into f. In this case, you would take whatever it is, 9, and say square it, and you'd get out an 81. What's going on graphically here is you're taking your G1 and you're plugging that into F, and you're getting F of G1. Which is, yes, F of G of X1, but we're just saying, just call it G1 because it's going to make things just slightly easier for what I'm about to do. Everybody with me? Are you not believing any of this? Okay, so you plug in an X2, you go to 3, and you plug that into G, and you get some G2. You take that G2, and then you plug it into your F, which means up here we'd be squaring it, but whatever. And you get your F of G2.
But
What's that?
we're gonna rename those as well.
No, we're not. We won't need to. We won't need to. I considered doing that, and I was like, nah, we're just going to do this. We're going to do this. So now here's the whole idea is we want to try to turn this expression into something that's actually easier to evaluate than having to take any given function and plug it into the difference equation. And what we're about to get is something that will do that. So first thing to notice here. So this is what's going on graphically. Everybody with me on that? I would like to get rid of these two pictures.
Yeah.
I did this deliberately just to really beat in the case that we're plugging something into one function. We're taking those outputs and plugging them into the new function. And remember, one thing I did here is I said g of x1, we just renamed it g1. We said g of x2, we've renamed that as g2. And so now, let's look at this thing again. We're taking the limit as x2 goes to x1 of f of g1 minus f of g2 over x1 minus x2. Yes? And that is the derivative at x1. Okay. Check this out. This is the same thing. Well, maybe it is, maybe it's not. I want to ask you, is this the same thing as this? F of g1 minus f of g2 over 1 times 1 over x1 minus x2. Is that the same thing?
Yes. Yeah.
Right? It's exactly the same thing. I just rewritten it. But as long as whatever I put here, as long as I put it here, it still remains the same, right? Mm-hmm. And so I could do something like this. Yeah? It is the same thing. Huh. That looks almost exactly the same as this, doesn't it? It's like if instead of plugging in an x into f, and I plug those in, right? What are we doing here? Well, that's just the difference quotient, right? Here's g2.
Oh,
here's f of g2. Here's f of g1. And what's going on over here? Well, remember how we got that. This was my g function. I plug in an x1. I should have kept this up. Here's my g1, which is what you got when you plugged in the x1 into g, right? x2 is what you got when you did this. There's your g2. G of x2. Probably should have just kept it without doing this, but anyway, whatever, right? Everybody get that? What's going on here? Like this, and what happens as x2 goes to x1? Well, let's just see. G is dependent on the x's, right? That's what we're doing. We're plugging in x's into here. G is going to change. So as x2 goes to x1, G2 drops down to G1. Right? And so this right here is the difference quotient for this guy. Right there.
But it's going to x1. It's the limit going to x, not the limit going to g1, right?
Oh, gee, I'm sorry. Sorry. Yeah. Here. As x2 goes to x1, G2 goes to G1. And so what you have here is this height. There's your change in F over your change in g.
Yeah. Yeah.
And so this is delta f over delta g. The delta g is going here, that's going there. This is the derivative, isn't it? Like, we could rename that x, and you'd have the derivative of f with respect to x. And we're just calling it g, it doesn't matter. But that is the derivative. This guy right here is that derivative, right there. So it looks like we have a product of two derivatives right here. Indeed, that's what we have, and this is what the chain rule is going to give us. So everybody got this? Yeah. I shouldn't have erased it in the first place. I probably shouldn't have done all this G1, G2 stuff. Like, really, and I'll be very explicit here, just in case. So the limit, as x2 goes to x1, of f of g... No, I do want to keep it this way, at least for this part of it. G2 over G1 minus G2. Times this stuff, which is g of x1 minus g of x2 over x1 minus x2. These are multiplied together. So the limit of a product is the product of the limits. Yeah? And so obviously this is g prime, right? This is the derivative of g at x1.
Yeah.
Yeah? This, though, you might say, well, wait a minute, this is just a constant with respect to x. Well, no, because I just redid this, right? Like, as x moves, g moves. Do I need to draw it again? Right? There's your x1 and your x2, and there's your g's, right? There's your g1. g1 and g2 are dependent on x. So as x1 goes to x2, g2 goes to g1. In fact, I could rewrite this by saying that's the same thing as this, isn't it?
Yeah, because they moved.
Like, that's what it means. As x2 goes to x1, g2 goes to g1. So you will get the same thing if you take this limit. What I'm saying here is that since these guys are the same, the limit of x2 going to x1 with something involving g and f or whatever is the same thing as the limit as g1, g2 goes to g1 of the same stuff.
Yeah.
Right? Okay. Okay. Now we have it. And this is something that that's actually useful. Because this is the derivative. So remember what I said, right? This is like the change in f over the change in g. And so this is, I should have done a recall how we did this before. This is df dg, or f prime with respect to g. This will be much more clear later, trust me. And this is the derivative of g with respect to x. dg dx. This, my friends, is the chain rule. Now, here we go. So, get ready for it. All that I said, pretend that every x1 was just x. Yeah?
Yeah.
Okay, so we'll do that. Now watch. Now, right now, that was the proof, kind of. The book has a completely different proof, and it's ridiculously rigorous. It's like, it's intense, man. Like, good luck. It's on page 161. Have fun with that. I wanted to do it my way. And this notation here, right, is very much like the difference quotients that we set up. Because remember the definition of this thing. Normally you have delta y over delta x, and you're taking the limit as delta x goes to 0, right? That's what y prime is. Another way of writing that is dy dx. But remember we had those different, I just added this g difference in there, right? And that's what's going on right there. Okay, so we had the change in f over the change in g, and we took the limit as the change in g went to 0. And we were multiplying that by the limit of delta g over delta x, the limit as delta x goes to 0.
Yeah.
And what that is, the way we write that is dfgg times dg dx. So that's all that means. Now practically, what does that mean? Well, and this is the way we're going to do this. F of g of x prime is, you take the derivative of f, and you pretend that g is just a variable in and of itself. Or like you could pretend that the whole g is just like x or u or something like that. If you're confused, don't worry, we're going to make all of this clear. In other words, you take the derivative of the outside stuff and you leave the inside stuff alone, and then you multiply that by the derivative of the inside stuff. This is the chain rule. There's two different ways of writing it. This is not so much useful right now, but later when you're doing multivariable calculus, this notation is really, really helpful. Right now, it's kind of nice because you can see that's what we did with the. Remember, we were trying to find df dx. That's what we're doing. We're trying to take the derivative of f with respect to x, but it has something in it, and so we just kind of did this type of thing, and said, well, if you throw a g in there, that'll make your life easier, right? And we can actually compute that stuff without having to actually take a limit. And that's what that is. So it's kind of nice to see that's where those differences came, we brought those differences in and stuff like that. But practically, this is how you're going to compute it. Okay? Now, the best way of doing this is to do an example. Well, so, do I want to do that? Yeah. So another way you could think about this right here is whatever that stuff is, you could just pretend it's just one single variable. And then when you take the derivative of it, you just pretend that it's just or just x, or just one variable. You'll see that in just a second when I kind of demystify all of this stuff. So this thing right here, let's go back to h. We said h of x was the same thing as f of g of x, where f was x squared, and g was my 2x squared plus 1. And so what this says to do is that if you want the derivative of it, we take the derivative of the outside stuff, leave the inside stuff alone. So let's just imagine that we just had an f of u, which would just be u squared. What's the derivative of that?
2u.
Just 2u. And so the u here happens to be this stuff. It's all of that stuff. So this would say the derivative of this then would be 2 times whatever's in there. So 2 times all that inside stuff, which is 2x squared plus 1. Then we multiply that by the derivative of the inside stuff. And so what is the derivative of the inside stuff?
4x.
4x. So we have 2 times 2x squared plus 1 times 4x. Why don't I bring all of that over here and I get 8x times 2x squared plus 1, which multiply that out and tell me what I get.
16x to the third plus 8x.
Is that the same thing as that?
Yeah.
Oh, so it works. All right. This may look a little, and especially, so I just wanted to prove it. This is actually a very simple thing to get in the habit of doing, especially with the way I'm going to say to do it. Are you guys, how do you feel about this so far?
Does the chain rule work when you have more than 2 functions
Woo! Boy, does it. So, yeah, we'll get to that in just a second. That was the next thing I was going to talk about. But first off, let's do an example. And this is what I mean by... So, one thing we're not going to do, you'll notice I'm starting at 7, not at 1 through 5. Because it'll give you something like this. Those types of questions give you something like this. And it'll say, rewrite this as a composition of functions. And so you could say, okay, f of x is like, I guess, an h of g of x, where the h is the outside stuff. So the h of x would be what? What's the outermost thing?
Square root of x.
Square root of stuff, right?
Yeah.
And then the inside stuff, g would be, I guess, my 1 plus sine x. And then it walks you through doing then there's the derivative of this, and so you know that the blah, 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 blah. I don't really, I'd much rather just do it the way that I'm about to say is, okay. So chain rule, I didn't write this up here. Chain rule, when you have a function in a function, and you take its derivative, listen to what I'm about to say. You take the derivative of the outside stuff, leave the inside stuff alone. Then you multiply by the derivative of the inside stuff. If you have those words in your head as you do these, you'll be good to go. So take the derivative of the outside stuff. What's the derivative of square root?
1 over 2 root x.
There, good. Okay, 1 over 2 root stuff. So take the derivative of the outside stuff. Oops. Okay, so we're computing the derivative. Leave the inside stuff alone. Then multiply by the derivative of the inside stuff. So, and you can see, you're just one at a time. You're just taking one little step at a time, so don't get overwhelmed here. One thing I don't want you to do is to do this and then go, okay, so f is h of g of x, and then we have a h prime of g of x times g prime of x. Okay, h prime is this, so h prime is 1 over 2 root x, and so h prime of this would be 1 over 2 root gx times g prime x, and then it's no. It's take the derivative of the outside stuff. Boom. Leave the inside stuff alone. Multiply by the derivative of the inside stuff. There's the inside stuff. What's the derivative of that?
Cosine x.
Yeah,
Just cosine x. 1 plus sine x. This is just cosine x. And so I guess, that's good, but I'll just rewrite it a little bit nicer. So we have cosine x over 2 root 1 plus sine x. Everybody got that? Not too bad, right? It looks crazy with the D's and the G's and but I don't really find this to be very effective. Like to do a bunch of exercises like identify this, identify that, and then try to, we could, but I think this is much more clear to just think about it like this. Take the derivative of the outside stuff, leave the inside stuff alone. Multiply that by the derivative of the inside stuff. So now, let's do this one. This guy. But now instead of 2, it's 20.
Okay.
So we're going to take the derivative of the outside stuff.
Yeah.
What's the outside stuff?
It's just
That,
so
right?
20 goes down.
So this is take the derivative of the outside stuff.
Yeah.
Leave the inside stuff alone. Multiply by the derivative of
For
the inside stuff, which as you're doing this, you'll just jump to the chase and just write that. Unless it's really complicated, in which case you'll want to do, so what did you say, 4x?
Yeah.
And so why don't I bring this guy over here? 4 times 20 is what?
80x.
80x times 2x squared plus 1, 19. Much easier than multiplying it out, right? Yeah, okay. So that's how that works. Everybody got that?
Yeah.
Okay. Why is it called the chain rule?
Because
If you have more, it makes
bunch
a
of
chain.
functions.
Because what?
If you have more functions, it makes like a chain.
Yeah. And so, yes, so check this out. So if we have f of g of h of x. So this is, Victor, what you were asking. You want to take the derivative of that. It's exactly the same thing. Take the derivative of the outside stuff. Leave the inside stuff alone. Multiply that by the derivative of the inside stuff. So, the derivative of the inside stuff. Which is now, what? Wait for it. GHX. Take the derivative of the outside stuff. Leave the inside stuff alone. Multiply that by the derivative of the inside stuff. And so yes, it forms a chain, basically. You peel off the outside each time, right? Okay. This is, remember back to Algebra 2 when I was like, it's so important that you could identify, and I've been calling it this since Algebra 2, outside stuff and inside stuff. Right? Like, what's the outermost thing? So, like, if you were going to undo this, if you're trying to solve this for x, if you're trying to solve this equation for x, you would undo the outermost thing. The outside stuff would be the first thing that you do, right? You would take the square root like this. And then you'd undo, a bit and a bit. Root y minus 1, 2x squared. Then you'd undo this, right? And, interesting. We could have written this as a composition of a ton of functions. In fact, I'd like to do that right now. And let's just to check if this chain rule really is a chain, right? So let's think of h of x. So the very first function we could think of is just x squared, right? And so I'm going to call that a of x. It says as I'm trying to evaluate this thing, it says take your value and square it. Okay. Now, so then what do we do with it?
Multiply by 2x.
So 2x, you take whatever that thing was and you multiply it by 2. Then you do what?
X plus 1.
So you take whatever that is and you add 1. Then what's the last thing you do?
Square it.
You take what?
If we square 2x, we get 4x squared.
No. Okay, so look. So here, let's break this apart. The very first thing is a says take it and square it, right?
Yeah.
So a of x is the same thing as x squared. Then you have to multiply it by 2. Says multiply this by 2. You take whatever that thing was, you take your a of x and you multiply it by 2, right?
Yes.
Then you take whatever you had, you take it and you add 1 to it, yeah?
Yep.
Then you take that entire thing, whatever that thing was, and you square it, right?
Yes.
And we'll check that when we go to compose these. We'll make sure that that's what this is. My claim was that h of x is d of c of b of a of x. Jeez. This is terrible. Okay. Okay?
Yeah.
Let's check it. Okay. Let's check d of c of b of a of x. That closes b, close c, close d. Okay, a of x was x squared. So I could replace a of x with x squared. B of x says take whatever x squared is and multiply it by 2, right? So take whatever is inside, multiply it by 2. So that would be x squared times 2. C says take whatever that thing is and add 1 to it.
Yeah.
So that would be the same thing as whatever that thing is and add 1 to it. D says take this, whatever it is, and square it. Is that the same thing as H? Yes. Okay, cool. Okay, cool. So, chain rule says if I want the derivative of this, take the derivative of the outside stuff, leave the inside stuff alone. Multiply that by the derivative of the inside stuff. But that's a chain. So take the derivative of the outside stuff, leave the inside stuff alone. Multiply that by the derivative of the inside stuff. That's also a composition. So take the derivative of the outside stuff, leave the inside stuff alone. Multiply that by the derivative of the outside stuff. Okay, so let's get derivatives. A prime is what?
2x.
B prime
2.
is 2. C prime.
It's 1.
D prime.
2x.
Okay, so let's see. A prime, let's work our way over. A prime is what?
2x.
Okay, so here's 2x. What is B prime of any number? B prime of smiley face.
Always 2.
It's always just 2, so it doesn't matter what's inside of it. It's
Yeah.
just 2. Okay, cool. What
That's
about
always one.
C prime of frowny face?
Just 1.
Is still 1. Doesn't matter that all this other stuff is in it. It's still just 1. What is D prime of CBAX? So
2x times 1. Wait, no.
2 times whatever's in there.
Yeah.
Right? So of CBA. So the composition A of C of B would be 2x squared plus 1. Right?
Yeah.
Yeah.
And so it would be D of 2x squared plus 1 would be 2 times 2x squared plus 1. Yeah? So 2 times 2x squared plus 1, which is 4x times 2.
It's 8x.
So, yeah, 4x times 2 is 8x. So 16x cubed plus 8x. Ha. Ah, nice. Okay, cool. So again, like, that's another reason I don't like those identify the composition. It's like, you could do this 1,000 different ways, right? The obvious way is, well, I could deal with this function right here. That's a function I could take the derivative of easily. So I don't need to keep going and making it more granular, because obviously that's just a real pain, right? So you have functions and functions. You could use your mind to say, okay, look, I don't need to go farther beyond that because that's an easy one to do. I could just take the derivative of it and it's just 2x or 4x. And my life's easy that way. Everybody with me on that? All right, let's do a hard one. Here's an example. F.
That one wasn't the hard one.
No. Well, I mean, yeah, actually, that was probably, yes. I think that was much harder because we're making it too granular, right? But here we go. All right. We want the derivative of f. So, it's a composition. Take the derivative of the outside stuff.
So cosine.
So cosine, leave the inside stuff alone. Multiply that by, and in this case I am going to go ahead and write it out, the derivative of the inside stuff. So, what is the derivative of that?
Oh, well, it's 1 over 2 times...
Yeah, and so I'm seeing outside stuff, inside stuff.
Yeah.
So, let me go ahead and write another line because I don't want to mess this up. One thing, here's a pro tip. Go ahead and take the time to write that stuff because it's some of this stuff right here can be so complicated that you get to the end of it and you think you have the answer, but you forgot to bring this guy down with you.
Yeah.
That will mess you up every time. So, it pays to just keep writing this stuff here. Did you catch what I meant, Victor?
Yes.
Okay, cool. So, take the derivative of this. I see outside stuff and inside stuff. What's the derivative of the outside stuff?
1 over 2.
1 over 2 of that stuff. So take the derivative of the outside stuff, leave the inside stuff alone. Multiply that by the derivative of the inside stuff. What's the derivative of that
2x.
stuff? That's just 2x. Now let's put everybody together. we have cosine on the top and a 2x on top. So how about 2x cosine? On the bottom, I have a 2 and a root.
Cancel.
I could cancel a 2, and that's what I'm going to do. So we have x cosine root x squared plus 1 all over root x squared plus 1. That's the chain rule. And if you just keep applying it, right, like if this were like sine squared, well, you just keep going, right, and so on and so forth. This turned out to be easy, but yeah. Okay, everybody cool with that? Okay, you're gonna get a lot of practice with this. It's also gonna show up like where it's not just that thing by itself. Like it's not just a composition that you want to take a derivative of. Here's an example. Number 20. Y equals, let me check time. Okay, we have plenty of time. X squared plus 1 times the third root of x squared plus 2. And we want to take the derivative. First off, the first thing I'm going to do is say, I wouldn't even have copied it down this way. I'm going to say, you know what, this root, I'm going to rewrite this like this. And probably for the rest of the time you're in calculus, you want to do that. Like, it's just going to be easier on you. The only one is square root. Now you have it in your head that the derivative of this is this. Right? So square root's okay. If you see square roots, you could probably keep it like that. Cube root, not so easy. It's much easier to deal with it as a power. So, okay, derivative, what do I do?
Well, it's 2 multiplied by 10.
Yeah, and so the outermost thing I see is a product of two functions. So we're going to need to do the product rule on those two functions. Okay, so product rule says take derivative of this one, leave that one alone. So I'm just going to do it like this. Prime, leave that one alone. Add that to what?
I'll leave the first one.
Leave the first one alone.
And then the derivative of the second.
And the derivative of the second one. So x squared plus 2 to the 1/3. Now this one's easy. This is just, what's the derivative of that?
2x.
2x times x squared plus 2 to the 3rd. This is plus x squared plus 1. Okay, derivative of this. What's the outside stuff and what's the inside stuff?
To the 1/3 is the outside stuff.
That's that. So take the derivative of the outside stuff and what do I get?
So negative, or 1/3
1/3 times whatever that stuff is. I'm not even looking at it.
Yeah.
Right? And that's how I do this. I don't even compute what's in there until later. And then what does the power go to?
Minus 2/3.
Minus 2/3. Did you follow that, Victor?
Yeah.
And you want to argue? You think it's not? No. Okay. Just make it true. Make it true. Okay. X squared plus 2. Leave the inside stuff alone. Multiply that by the derivative of the inside stuff, which is 2x. Technically, we're done. I mean, right?
Yeah.
You could do, although, you could say, okay, there's 2x, that's the cube root of x squared plus 2. Plus 2x x squared plus 1 over 3. That guy comes into the numerator or denominator and is squared. Now here's the thing. That's fine. Like on a quiz, that's cool. You just stop right there, everybody's happy. But if you're doing this work in a book, and the book has that as an answer, or if it puts it all over a common denominator, keep going until you get that or until you get whatever the book says. Everybody with me on that?
Yeah.
Okay? That's part of this. Like, make your answer look like the one in the back of the book.
Okay. Yeah.
Cool? Everybody with, okay? Okay. Okay, here's something interesting. Let's do this one. Actually, no. I want to make sure we have time to do this. So, here's one way. So let's recall last time we did this. Which we said, the derivative of tangent is the same thing as d dx sine over cosine. Yeah? And then what did we do? How did we do this? We said it's what and what and what and what, and let's do it.
Well, we use the quotient.
We use the quotient rule, which says
Derivative sine x.
So sine prime times
cosine.
cosine
Minus.
minus
Sine times cosine prime.
sine cosine prime all over
Cosine squared.
cosine squared. That gave us sine, gave us cosine,
Negative
Cosine squared.
negative sine
times sine.
And
times what?
sine.
What's the derivative of cosine?
Negative sine.
Negative sine.
And
Okay.
it's just 1 over.
Cosine squared. So that gave us cosine squared plus sine squared
Which
over
is just 1.
cosine squared, which is just 1 over cosine squared.
Which is secant squared.
Which is secant squared, which we could write if we wanted to. Either one of these ways is fine. Now, check this out. This is pretty cool. And pay attention, because you have a homework problem where you're going to want to pay attention. Another way you could do this is say, well, hold up, sine over cosine. Sine over cosine is the same thing as sine times cosine to the negative 1. Right? Like if you have something in the denominator, you could just write it in the numerator, but just raised to the negative 1 power. So, using what we've done today, what do we do?
So the outside stuff.
I want to get this down here. This is cosine squared x, which we said is the same thing as secant squared x. Okay, so, what's the outermost stuff?
It's just a product.
It's a product. So,
So it's
product rule. So,
it's the derivative of the first thing.
derivative of the first thing, leave the second thing alone.
And then derivative of this.
Then, do I multiply
Leave
it
the-
by, divide it, add,
To the
then
first thing times the derivative of the second.
first thing times the derivative of the second thing. So what's the derivative of the second thing?
Negative.
Well, wait, let's do this real quick, because I don't want to forget this. What's the derivative of sine?
Cosine.
Okay, so that's cosine times cosine to the negative 1. Oh, that's going to be nice.
That's just plain.
It's just 1.
It's just
It's
1, right? Because that's
to the
cosine
1
over
times.
cosine. Yeah, okay. All right, so, but 1 second. Now, this is plus sine times, okay, so now let's do this. What's the outside stuff?
Negative 1
Right, so how do I take the derivative of that stuff?
times negative 1.
So,
of
negative
the
1
stuff.
comes
So
down.
Negative 1 times this stuff.
And then what does that go to?
Negative 2.
Negative 2. Leave the inside stuff alone. Multiply that by the derivative of the inside stuff. So that's cosine prime. Okay? So let's make this a little easier. This is cosine over cosine. This is, I'm going to pull that negative all the way out and go minus, yeah?
Sine times.
Minus cosine
That's just negative sine.
becomes negative sine, so I'm going to bring the negative back over here. Boom.
Yeah.
Right? So we have sine times sine over cosine squared.
Yeah.
Right?
Which is something. Oh, it's.
There's a few different ways, and you see, this is the crazy thing about this. Like, you stop there and you check the back of the book, and it says secant squared, and you go. So you think, okay, well, cosine over cosine is always 1. This is sine squared over cosine squared. Yeah.
Which is
Which
tangent.
is tangent.
Which is tan, so 1 plus tan squared.
Which is secant.
Which turns out to be secant squared. Or you could have said, wait, hold up. This is the same thing. Almost have a common denominator here. And it looks like that's always going to be the way it's going to be But anyway, I'll let you guys figure that out. See, there's a common denominator. I just need to multiply both by cosine. Right?
Oh, yeah. Oh, that's interesting. Yeah.
Yeah, and so cosine squared plus sine squared all over a common denominator,
So it's 1 over cosine.
which is 1 over cosine squared, which is secant squared, which is 1 plus tangent squared.
Yeah.
Yeah. So again, if you get to some point and you check in the back of the book and it's not what you got, keep going until you get it. Okay? That's my one big request for this. I do want to do one more. All right, everybody got that? All right. Okay, this is number 24. And it's f of x over the square root of 7 minus 3x. Now, there's a couple different ways we could deal with this, because I want f prime.
Quotient.
You could use quotient rule. You could use quotient rule. Or you could do what we just did and say this is the same thing as x. Now, that's the same thing as, well, here, I'll just do it this way. So this is the same thing as this to the 1/2,
Yeah.
which means that's the same thing as that to the negative 1/2.
Yeah. Okay.
Right, so I could do 7 minus 3x, 7 minus 3x. And I personally hate the quotient rule because there's that negative in there, and I'm always afraid I'm going to mix the two things up. And so you could just do this anytime you have a quotient, you could just bring it up here. It's always going to be the case. Any function you have here and any function you have here, you could always write that as a product. It's just that the thing gets raised to the -1, and you could just use a product or use the product and chain rule on it. Does it end up being easier? I don't know. Maybe. I think you end up doing about the same amount of work.
Yeah.
It's just now you don't have to memorize a new rule, right? You could just basically blank the quotient rule out of your head altogether. That's what I did. I don't remember it. I always mess it up. And it's because of that negative. I hate that negative. Okay, so f prime of this thing then would be, and this is how I would do it. Derivative of the first is 1. Leave the second one alone. Add that to, leave the first thing alone, take the derivative of this stuff. That's the negative 1/2. Okay, derivative, take the derivative of the outside stuff, leave the inside stuff alone. So 7 minus 3x to the negative 1/2 plus x. Okay, so now parentheses are your best friend here. The negative 1/2 jumps down, and that, whatever it is, I don't care, gets brought down to what?
-3/2.
Negative 3/2, negative 3/2, and then leave the inside stuff alone. Multiply that by the derivative of the inside stuff, which is what?
-3.
Negative 3. Now let's see if we can clean it up a little bit, because I'm seeing we have a root. Maybe it'll clean up, maybe it won't. Negative makes a positive. 3/2, and there's an x, and that's in the denominator. So, I mean, technically you're done, right? And you could, if you want, write this with its root or not. 7 minus 3. It depends on what's in the back of your book, right? So that's positive. 3x over 2. And we could put that down in the denominator, whatever. I'm willing to bet that the answer for the one like this in the back of the book would be something like this. something like that, right? 3/2,
Yeah.
it's the same as the, yeah. And so something like that, or maybe that raised to the third, so that then you square, I don't know, man. Like they would probably do that. They would probably get a common denominator there and do like, okay, so you need a 2 down here, a 2 down here. And you'd need
Another
a whole one of those, so
wait.
7 minus 3x on the top, and then 3 there. Again, I don't care. I like 2 times 7 is 14 minus 6x plus 3x. And yeah, this is definitely what they do. They would definitely have it in the back of the book like this.
it looks nothing like
And it looks nothing like what you got, right? You're like, there's my answer. And you look in the back of the book, and that's not even done because you have a 14 minus 3x, 2 there, and then they probably write it like this. 7 minus 3x cubed. And so you look in the back of the book, and they have that, and you have this, and you go, oh man. But but this is part of your homework. Like, make sure, I want you to check that you got the right thing. So keep plugging along until you make it look like that. But on a quiz, you're done right here, as far as I'm concerned. Okay? Because that's how my answers are going to look. I mean, you're done. You can plug that into anything, and you're fine. That is what it is. So, everybody got this? Okay, this, you should have enough, and they do a good job with the way that they have these. Like, they get more complicated as you do them, and so you'll, it'll be easier to deal with as you move along. I didn't have you do that one. Yeah, okay. 84, I just want to say, is very much like what we just talked about. Only in general. I'll just say what it is. It says, use the chain rule and the product rule to give an alternate proof of the quotient rule.
Oh.
And so, in other words, they want you to say, okay, use the show what the quotient rule is, and then do the same thing, but now
Oh, yeah, that's
do that, then just take the derivative of this, and you'll need to manipulate it until you make it look like the quotient rule. Not hard, but it could be, you could, miss what they're trying to get you to do. So, that's it, guys!